The subject of this video is the paper called Learn by Challenging Yourself, Contrastive Visual Representation Learning with Hard Sample Generation. The authors are from University of Pittsburgh, George Mason University, and University of Notre Dame. And it falls into the category of works focused on utilizing data without labels with a focus on contrastive learning. The abstract starts by talking about the motivation of this work. CL, or contrastive learning, requires learning on vast quantities of diverse data to achieve good performance, without which the performance of CL will greatly degrade, which is kind of a redundant sentence here. As it is clear from the title of the paper, which has sample generation in it, this paper is mainly trying to address the problem of contrastive learning algorithms requiring large amounts of data in order to perform well. And the methodology they propose is centered around hard sample generation. They propose a two-approach method that works by generating good samples and joint learning of this generation mechanism. So this two-approach generation method, the first approach of which is going to generate hard samples, which is for training the main model. And then this generator is jointly learned and will dynamically, on the fly, customize hard samples based on the training state of the main model. They will have a pair of data generators that will basically generate similar but distinct samples as positive pairs. Now, similar but distinct samples here refers to the fact that mostly in contrastive learning you have one image or one data point and you will augment it in two different ways, which means that the images are different or the data points are different, but just because they are basically the same image going through a random or probabilistic augmentation, they still share a lot of semantic context. Instead, you may want things such as basically two images or two data points that are coming from the same class, but they are not transformation of the same thing. So similar but distinct is a term here which is referring to two data points that basically are from the same class, but they are not the same data point going through an augmentation, and that they have the semantic diversity required for a good performance to be achieved by the model. Their work results in a 5% accuracy improvement on image 100 and cipher 10, more than 6% on cipher 100, and these are for the linear classification. Up to 2 times data efficiency and 5 times data efficiency for transfer learning, the previous one for linear classification, was achieved. The introduction talks about the motivation of these works, and in this part, training CL with scarce samples leads to drastic degradation in the quality of learned representations because of insufficient contrast between the diverse samples. Authors paint a better picture of the motivation behind this work. In another sentence, they mention, without diverse samples to discriminate from, the proxy task becomes relatively easy and the model can achieve high accuracy on the simple task without the need to learn high-quality discriminative representations. To further motivate this methodology with practical examples, consider cipher 10. When you do it without labels and then fine-tune the trained model on 1% of the labels, which means 500 samples, there's a 84.99% accuracy. However, if you consider only 10% of this data and then fine-tune it with the 500 labeled samples, the accuracy drops dramatically, which means that for the cases where a large dataset is absent, it is crucial to achieve a data-efficient contrastive learning methodology in order to increase the efficacy. And aligned with this goal, they propose a framework for generating this data for a contrastive learning pipeline. Let's go through the overview of this approach. Their framework consists of 2 approaches. The first one generates hard samples for the main model. These samples dynamically adapt to the training state of the main model. So they are not just some fixed hard examples. They are examples that are hard, and the definition of the hardness of example is based on the current state of the model, which will basically be leveraged by this generation mechanism in order to produce samples that further increase the representativeness of the model when used in training. Thus, this could be considered an adversarial approach that explores the weaknesses of the main model and forces it to learn discriminative features. Now, the second component of this is an approach that generates 2 similar but distinct images as hard positive pairs. So in the previous approaches, or compared to the mainstream contrastive learning area, when one image is used by 2, basically by applying a probabilistic transformation twice and obtaining 2 images, while these 2 look different, they still share the same identity. There are works such as the work called With a Little Help from Neighbors and things like that that basically use a buffer or a group of examples or nearest neighbors to try to find a better instance to contrast against, but this paragraph refers to the mainstream contrastive learning domain. They, however, in this work, form hard positive pairs by generating two images of distinct identities but with similar objects without using labels. And we will talk about how they do that. So this joint learning is the main contribution of this methodology, meaning that these positive pairs also become harder by decreasing their similarities. All in all, the contributions are a data-efficient contrastive learning framework, dynamic hard sample generation, and hard positive pair generation without using labels. This part contains the related works, which we are going to ignore at this point. And now let's talk about joint contrastive learning with hard sample and hard positive pair generation. So their method is focused on generative adversarial network, or GANs. And the first thing they want to show is that if you just consider it as an unsupervised approach such as SimCLR, and if you just use GAN plus SimCLR in order to just generate additional examples, the performance is actually going to drop and it's not going to increase. In other words, simply using a GAN pre-trained on the same dataset as contrastive learning to provide additional synthetic data to the main model cannot effectively improve and even degrades the learning representation. They conjecture that this is because the synthetic data has intrinsically lower quality than the real one. So their solution is that they propose a min-max game and kind of learn the generator component jointly with the main component. And the point is, no additional training data is going to be used. They formulate this as a min-max game, which you can also see here as well. There is a contrastive loss component that the main model tries to minimize, and now a generator tries to maximize it. You would have a generator, which is a GAN. You have also the momentum version of it, meaning that it's a slowly evolving version called EMA. And you have these two that are first pre-trained with a discriminator D on a given unlabeled data. They follow a normal pre-training GAN objective to basically interact with this distribution and generate meaningful images. Afterwards, this joint learning process would begin. Now, G generates individually hard samples, and you have G and the momentum version of it collaboratively generating pairs of hard positives. So G would generate hard samples, and with GEMA, it will generate hard positives. And you also use the real samples from the dataset. And together, it forms a batch. And then the model tries to minimize the contrastive loss. Now, what is the process for hard sample generation and joint learning? Considering the Gaussian distribution, as it is usual in GANs, you would sample a Z from this probability distribution, which is a Gaussian defined with the average of all 0 and the covariance matrix of 1, meaning identity. So we draw a set of vectors Z's from this domain, and then basically would feed them to generate these examples, which are the generated examples. And this way, using G and the GEMA, you will have two basically samples that are multi-viewed examples of the same identity because you are using the same Z in them. As I showed before, it is clear that a min-max game or an interactive or alternating optimization system is required to jointly optimize these generator and contrastive model, and simply using a generator to provide additional synthetic data is not helpful. Now consider that theta is the set of parameters of the main model and omega is for the generator. One critical detail is this: updating omega, which comes from here, requires gradients to be propagated through the generator as well. Now one point here is that those two positive examples were also going through a certain transformation. Now these transformations have to be differentiable in order for the gradients to be able to get past that point. To do that, they were using a library called Cornea, which provides such differentiable augmentations. They would use this generator, and then they also use this slowly evolving version GEMA to basically generate similar but different images, meaning that images that have the same identity but are different. Meaning, per the description of this paper, are similar but distinct. So they sample a ZI from that Gaussian distribution and would feed it to G and GEMA and then they would produce x2i minus 1 and x2i as two samples, and would basically consider the same pseudo label for them. G is learned in joint learning, but GEMA does not. GEMA is a momentum-based training. So when you want to generate n samples with n divided by 2 positive pairs, you sample n divided by 2 ZIs, and you would generate n raw samples, half of them basically coming from the G and half of them from the GEMA. And then you would also apply 2 transformations, and then you would also add them to n real examples from the dataset. After going through the transformations, you would have 2n real examples, so you would have 4n examples overall in the multi-view batch of yours. So they will have partially pseudo-labeled contrastive loss here, which if you look at it, it's basically the same as supervised contrastive loss. The point is that if an image is real, then its counterpart is going to be the other view coming from the other transformation on the other on the image that is applied to is going to be considered the same pseudo-label as it is. But for the generator of examples, you would have 3 other examples in this batch that are going to have the same label as that one. So because of this intermediary approach, they call it partially pseudo-labeled contrastive loss. Then they would plug this partially pseudo-labeled contrastive loss into the min-max problem, and then jointly optimize everything. Now they describe that the formulation of loss is going to be something like this, and what you can see that you have to generate individually hard samples, meaning that the multi-view versions of the result from G or GEMA has to satisfy the constraints on this contrastive learning. So this would lead to individually hard samples being generated. And the same goes for positive pairs, obviously because of the interactions of these elements, these 4 views coming from the same Z. They evaluated the results on 5 datasets: ImageNet 100, Cypher 10, Cypher 100, FashionImageNet, and ImageNet 10. They used ResNet 18 and a 2-layer MLP as a model, mapped it to 128-dimensional representation. And for metrics, they focused on linear classification and transfer learning. They trained the classifier for 500 epochs with Atom Optimizer and 3E-4 as learning rate. Considering linear classification in ImageNet 100, they show that, let me change this. They show that when using different amounts of training data, meaning 100%, 20%, and 10%, the proposed method is going to outperform SimCLR by these margins. And as you can see, the less data we have available, the higher would be the performance gap between this model and SimCLR as a contrastive learning baseline. The same was shown on some other datasets as well. The next evaluation method was transfer learning. So they transferred it to target tasks by pre-training on ImageNet 100, and then they reported the linear classification performance on the target task. You can see that this way they also discuss the fact that there is a 2 times data efficiency in some cases. And here is an example why. As for the ablation studies, this figure 4 is important. They show basically that all of these have to be combined, meaning that just using the hard positive pairs and hard examples or standalone GAN is not going to lead to an improvement. They also show that longer training sequence would lead to a higher advantage in the proposed model than the other ones. This is an example of these progressively harder pairs that are being generated, as you can see. As the training progresses, even though they still share the same identity, they become different picture-wise. So you can see this one is an example of this.